So I want to talk to you today about ARM64e, which is an ABI for pointer authentication on ARMv8.3. So what do any of those terms mean? ARMv8.3 is an official ARM extension to their 64-bit architecture that was released a few years ago. We started releasing it at Apple in shipping hardware, starting with the iPhone XR, generally the A12 and later. All of our ARM chips across the board are now capable of using this. And it's not just a hardware feature that it's shipping, it's actually a software feature as well. All of the system software, starting with iOS 12, I think, on these devices is using ARM64e. So this is across the board, this is real, this is shipping, this is an actual product. It's not ABI stable yet. We are still looking for a lot of ways to strengthen it. We are encouraged feedback. We'd love more security analysis, that sort of thing. We really want to hear what you have to say. I described everything on this in my slide title now, except the big one, what is pointer authentication? It's a security mitigation technique. Mostly what it provides is control flow integrity and a limited amount of data integrity, but mostly just in order to protect control flow. The basic idea behind pointer authentication is that you are signing and then authenticating pointers in order to prevent attackers from just turning those pointers into arbitrary places in the memory and using that to escalate memory corruption bugs. Most security attacks, most exploits begin with some sort of memory corruption bug. That's like a buffer overflow or a use after free. And of course, ideally, these bugs wouldn't exist. We'd all be using safe languages. We'd all be, enthusiastically embracing safe practices like static analysis. And by no means is anything that we're going to talk about today a replacement for any of that. That's still obviously where we need to go in the long term. But practically speaking, we have literally billions of lines of code in these languages today. Even if you're writing your entire application in a safe language like Rust or Swift, you're still interacting with a lot of unsafe code from the system. You are in that same process. You are in that address space. You are not a safe environment. That's why this kind of mitigation technique is so important right now and why it's going to continue to be important for really the foreseeable future. So, like I said, most exploits start with some sort of memory corruption bug, like a use after free. Well, if you've got a use after free, as an attacker, you can almost certainly use it to crash the process. Great, congratulations, you have a denial of service attack. That's a reasonable thing to get, but usually attackers are after something more. They want they want to achieve something more than just crashing the process. They want to access sensitive information, read it in, ship it over the network, and so on. These are things that the process, hopefully, is not doing automatically for you. It's not part of the normal control flow. So in order to get the process to do that, they have to hijack control flow in some sense. They need to run their own code. So for example, here's a little payload. It's basically synthesizing a write call. It's going to write some data from a password file that is presumably already loaded into memory, right? Well, used to be time was that you could just, write this payload into memory somewhere and execute it. Thankfully, we haven't been in that particular state for a long time. Modern systems are a lot better than that. You can't just write executable stuff into memory unless you have a JIT. Let's not talk about that. So if you want to get this kind of code payload, and you can't just have it, but so what attackers have learned to do instead is assemble it from a bunch of different places in memory. So you have a bunch of different functions in memory. These are called gadgets. All of the gadgets do individual bits of the thing that you want to execute. And together, cumulatively, they have the effect that the attacker wants. So an attacker just finds these gadgets, and then they need to execute them in the order that they want. And in order to do that, they have to hijack some sort of control flow. And there's two main ways that they do that. The really common one is return-oriented programming, where they redirect a return. The other one that's it is seen in the wild, but I think it's going to be seen more and more, is jump-oriented programming where you're redirecting some sort of call, some sort of indirect branch. The goal of pointer authentication is to block this from happening by breaking those attempts to redirect control flow. The basic idea is that we add a signature to every code pointer and some data pointers that are necessary in order to further protect code pointers. And then whenever we want to use one of those things, we authenticate it and verify that it hasn't been tampered with or replaced. In ARMv8.3, that signature is stored in the upper bits of a 64-bit pointer. The number of bits exactly can be configured by the operating system to allow the memory needs, as the memory needs of the system grow over time. So what is a signature? Well, it's basically just some sort of cryptographic hash function. So you take the actual pointer bits, you hash them in some reasonably non-reversible way, and you end up with this a bunch of signatures, and then you just stash in the top bits. Basic idea. Well, if you just did that, attackers would just need to know the pointers, and they'd have to figure out what your hash algorithm was, and then they'd be able to synthesize the signature from scratch, right? So you'd have gained absolutely nothing, because the attacker would be able to synthesize a properly signed pointer for anything. So another input to the hash algorithm is data from a secret key register that the attacker can't access directly. It's not even available in the address space by default. It's not directly readable by the process. And so this is just some, can basically be random bits. It's just inputs to this hash. As long as the key values change, which hopefully you can have them be different on different devices, on different processes, and et cetera, then you'll get a different hash algorithm, a different signature for different things, and you won't be able to reproduce this reliably outside. So that prevents attackers from easily synthesizing a forged pointer, but it doesn't provide all the protection we need. So there's another input into this that's called a discriminator, which is just, again, 64 bits of, it could be arbitrary data, but it's usually arbitrary data associated with why you're signing this particular pointer. And I want to go into that a lot because it's actually really important. So why is this necessary? So like I said, signing with the key alone means nobody can forge it, but it doesn't stop you from replacing a pointer with some other validly signed pointer, as long as it's been signed with the same key. And it turns out that that's actually something that security researchers have shown is quite easy to do, that you can make gadgets out of things that you already have, valid, reasonable reasons to have signed pointers in your process, out of the starts of functions, out of, places that you might be returning to, et cetera, right? So it's vitally important to be able to stop not just forging signatures, but also this kind of substitution attack. And so substitution only works if the inputs to the hash besides the pointer are the same. So that's the key and the discriminator. There's only a small number of keys that the hardware is going to support at one time. So the main way that you get differentiation between different signed pointers is by using a different discriminator value. Ideally, every different reason that you might conceivably have for signing something would use a completely unique discriminator. And such that, you'd be able to confidently say that, okay, look, the only thing in the entire address space that is signed the right way that's going to be past this particular auth that has to happen for this particular reason in the program. The only things are something that some human would actually look at and say, oh yeah, that should totally be able to call that thing, right? Pointer authentication is, of course, compiler automated technique. So we don't have that kind of perfect user-oriented information about purpose and deep truth about the program. So we are limited by the knowledge that we have, and we're limited by the sorts of things that the language design allows us to do with a particular pointer. Often there are restrictions on things, and I want to get into that because it's very important. So like I said, most of the protection of pointer authentication is provided automatically by the compiler, and that means it's part of the ABI for particular implementations of things. So the compiler automatically assigns return addresses. It automatically makes sure that switches are done correctly. It handles things around symbol imports and makes sure that you can't corrupt things that way. But also for core things like C function pointers, C++ virtual tables, anything that involves indirect control flow in the process is part of the language ABI and has to be thought of carefully when you're talking about pointer authentication. So the ABI rule is going to specify what key to use and how to compute the discriminator. In theory, the discriminator on ARMv8.3 arbitrary 64-bit value. But in practice, for ABI reasons, it's going to need to be more restricted so that we can, usefully and reliably sign these things in some more restrictive situations. For example, the loader needs to be able to sign, some pointers that are going to be written into global memories, like in a vtable or something like that. For these sort of practical reasons, the way that discriminators end up being computed in practice is a combination of just two factors. The first is whether to use what we call address diversity, and the second is the choice of a small constant discriminator. And then those two things get blended together. Address diversity means that the discriminator includes the storage address of the pointer. So if you have a function pointer and it's stored in a variable called x, and x is at address 1024, then 1024 is part of the discriminator. When you're using address diversity, it means that the same pointer, when it's stored in different places in memory, will have a different signature. That's a really powerful sort of thing to be able to say. What it particularly means is that it means that an attacker can never just harvest a validly signed pointer from one part of the program and then copy it over somewhere else. If at least one of those things is using address diversity, then the discriminators aren't going to match because the addresses are different. That's a very strong amount of protection. Unfortunately, we can't always use this. The big reason is that it's incompatible with memcopy. It requires additional work in order to copy this thing. It means you can't necessarily use this inside of a union, but it also means that things in C that require things to be memcopyable, you can't just all of a sudden make it non-memcopyable and break the semantics of C. The other side of this is a constant discriminator. So this is just a small constant integer in ARM64e. We've chosen to restrict this down to 16 bits because that happens to align very well with both a very nicely compact loader metadata, but also a very nicely compact instruction sequence that we can use to sign and authenticate pointers. So how do you pick a constant discriminator? Well, typically if you're a compiler, you're going to be deriving it from something about the program. So you can derive it from a declaration. So if I've got a field X, theoretically, if I was signing a pointer to this thing, then I could sign that with something a string derived from the fact that this is the field X of the struct F, right? That's a very precise amount of signature. Or I could derive it somehow from a type, right? So it's same thing, but I don't get to know about F or X. All I get to know about is int, right? Obviously, the first is better. It's going to be more specific to specific purposes, but again, language rules are going to prevent that in some cases because you can't break sort of abstract uses in the language. As an example of that, let's talk about C++ virtual functions. So C++ virtual functions are a great case for ways in which we can actually get very, very good discrimination by default. So there is no direct access to the contents of a vtable in C++. You aren't allowed to read the vtable pointer out and memcopy its contents or anything like that. Because the contents of the vtable don't need to be copied, there's no reason we can't use address diversity on all of them. And because there are abstract uses of vtables in C++ because of the of member function pointers. But member function pointers, there's a way to implement them in a way that doesn't totally subvert our ability to use good constant discrimination here. So as a result, what we can do is the constant discriminator that we actually use is derived from basically the mangling of the entire method name. So it's actually very specific to that specific declaration, and a different method with a different, that happens to have the same type, but has a completely different name and signature and base type or anything about it will have a completely different discriminator. So it actually is very close to the core idea of like every different purpose has a different discriminator. The other end of the spectrum, unfortunately, is a C function pointer. So the C standard requires that pointers be mem-copyable. They have to be a trivially copyable type, just like basically everything else in C. That means that address diversity is right out, because if you wanted to copy something with address diversity, you have to re-sign it from one discriminator to another. Furthermore, if you've got a function pointer that's stored in a variable, you can take the address of that variable, and that has to work, and you can access that thing. And the only guarantee that you get is that somebody's accessing it using an L value of the right type for that variable. And that means that when something is signed in that variable, unless you're doing a more complex analysis, you have to sign it using basically only information from the type. So declaration-based diversity is straight out. And it actually gets worse from here. So type diversity in practice is something that we can pursue, but there are a lot of practical challenges for that. And in our current ABI, we actually end up, while we are trying to improve this, currently we actually end up signing all C function pointers with the same value, with a 0 discriminator, which is quite a bit of a hole in our current approach. And it is something that we're trying to improve on. As a sort of temporary workaround, and in order to let people sort of opt into that declaration-based diversity, we do have some language features that allow people to use better discriminators for particular L values, particular declarations. To talk more about the code generation aspects of this, I'd like to invite up Ahmed.
Let's talk about what it entails to actually generate code for ARM64e. And so when you're trying to generate code for ARM64e, you're really trying to generate two operations. So sign, as John explained, it computes the hash of the pointer, and from a raw pointer, it produces a signed pointer. And authenticate does the opposite. So it strips the signature bits out of the pointer. It verifies that they're valid, and it produces a raw pointer. And so these are easy operations to represent at the IR level. So we have LLVM, put auth, sign, and auth intrinsics. And we can easily lower them to the ARMv8.3 instruction. So there's a PAC, which means sign, and Auth, which means authenticate. And so one interesting dimension where the architecture has liberty here is how verification failures are implemented. And so on ARMv8.3, how that works is when the auth instruction notices that the verification fails, so when the signature bits are not valid, it's going to set one of two bits in the resulting pointers. So we call them poison bits. So the resulting pointer is something that is guaranteed to never be addressable on an ARM CPU. But so when we're trying to use these operations, so auth and sign, we have some requirements to actually make them useful. So first, when you have an authentication operation, you have to make sure that the verification step actually happens. You want to make sure that an attacker is not able to just bypass the verification completely. And similarly, for the sign operations, you want to make sure that the pointer that you're signing is something that we actually have some degree of trust in. It's not something that the attacker also controls. And the fundamental problem we have with these two operations is that they necessarily deal with raw pointers, right? So if you authenticate a pointer, you produce a raw pointer, and then you sign a pointer, you take a raw pointer. And it's really hard to abide by these security requirements once we have raw pointers. Because these raw pointers are necessarily vulnerable, because there's no way to verify them. They can come from anything. And they can be exposed, for instance, when the register allocator decides to spell them. And that's a big problem, because now the attacker just controls the raw pointer. So it's really hard to provide guarantees when you have these raw pointers next to these operations. So what we can do instead of providing like absolute guarantees about any of these operations. It's just focus on the actual uses of sign and auth that matter to us when trying to implement ARM64e. So again, we're trying to do control flow integrity. And so really what matters mostly is any pointer that's used for control flow. So I'm going to talk about 4 interesting use cases that matter to this. There's a lot more, but we don't have a lot of time. So let's dive right in. So the first thing is control flow. So obviously, John mentioned C function pointers being signed and C++ vtable entries being signed. And so what that means is when you do a call, that's going to necessarily have to do an authentication operation. And so the way we do that is we have put-auth operand bundle that we put on indirect calls. And basically what that does is now the call instruction does a combined authenticate and call operation without exposing the intermediate pointer that's vulnerable. And so similarly, indirect branch is also something that's vulnerable. So we also want to add a pointer auth bundle to that. That's a little more complicated at the IR level because of the way we allocate uses. But that's fine. We can talk about that on the list. And then switches is also something that John mentioned earlier. So switches are more interesting because they can be lowered to jump tables, but that's only something that happens in the backend. They're not actually exposed to the IR representation. And so one thing that we could do is sign all the entries in the jump tables. But that's something that's very expensive because it would require turning jump tables into an array of pointers. And that means that we need reallocations. That means that they're not just small offset anymore. They actually have to be 64-bit values. So we decided it's too expensive to actually sign jump table entries. So instead, what we do is what we call jump table hardening. So we have this sequence in all jump table dispatch that guarantees the integrity of all the intermediate values. So we range check the index, we make sure to materialize the jump table address in a safe way, and all the way to the actual branch instruction, which now can be just a regular BR that doesn't do any authentication. And that's fine because we know that we control all the intermediate values that were used to derive the pointer. And so this is interesting because it's one of the cases where ARM64e isn't just pointer authentication. It goes beyond because we're really trying to do control flow integrity and more. So that's called control flow. So the next thing is sometimes you want to convert between different signing schemes. So if you imagine if you have a cast between differently typed function pointers, that's something that might happen. And so for that, we have a resign intrinsic. What the resign intrinsic does is it authenticates a sign pointer using key and discriminator A, and then it resigns them using the PAC instruction using key and discriminator B. And so this is a lot more complicated in some cases. So I'm going to talk about 2 problems. And to understand these 2 problems, we need to go into the details of how the instructions work at the bit level. So in the sign pointers, there's actually 1 bit that's not part of the signature. It's actually a selector bit of sorts that's used by the auth instruction to produce a proper kernel pointer. So in the kernel address space, all the pointers start with a bunch of 1s, and in userland, they start with a bunch of 0s, as we explained earlier. And so when we try to sign such a pointer, the PAC instruction is going to do the opposite. It's going to truncate all of these bits just to the 1 selector bit. So this works great when you have a valid authentication, but there's a problem when there's a resign failure. So if you imagine, the auth will first broadcast the selector bit to the address space bits, but then it's also going to poison this pointer because the signature bits are not there, are not valid. And so this gets a lot more complicated when you try to sign this pointer and try to resign, because then the PAC instruction is going to try to truncate all these bits into just the 1 selector bit, but it's also going to have to corrupt the signature because there's a mismatch between all of these sign extended selector address space bits and the 2 poison bits. And so this does achieve the end goal, which is that the resulting pointer is not something that's valid because the signature has been tampered with. But it's still a major problem because it means that out of an invalidly signed input, the resign sequence will actually emit something that has all the signed bits valid except 1. So that's a big problem. It lets attackers forge these pointers. So we mitigated this by checking for auth failures in the resign sequence. And so we guarantee that we only emit a pointer that doesn't leak the signature bit. So we will strip the pointer if there's an authentication failure. That's also problematic in certain cases because an attacker, if they're able to actually brute force this sequence, they can keep trying until they get something where all the address space bits aren't all the same. And when they find something that has that, they know that the resign succeeded. And so interestingly, that's not something that happens in a lot of usage of auth instructions, because most of the time, like when we do a call, we're going to do auth and then call immediately. So there's something that will check the result pointer immediately. But this is special to resigns and to tail calls for other reasons. And so instead, what we ended up doing whenever possible is we trap when there's an authentication failure. That's something we're looking to deploy. It's much harder to deploy, obviously. So that's resign. So another thing that we often do is actually generate a pointer to a constant that is signed as a constant initializer. So if you think about it, that's something that happens whenever you emit a vtable. And so for that, what we did is we added the LLVM per auth section where we put globals that are basically a wrapper global that's basically expressing a signed relocation to a symbol. And this is something that ideally should really be a constant expr, but we have constraints for downstream bitcode, so that's something we can talk about on the mailing list also. And so similarly, you also want to be able to sign a pointer to a constant, but do that in code. For instance, if you're trying to take the address of a function in C, and for that, you can also use the LLVM per auth global wrappers, and those we also have to lower them in an interesting way. So first, we materialize the pointer using whatever the Darwin convention, but then we have to sign that pointer immediately. And so here we also have combined operations. So this is something that only exists in the backend, materialization of pointers, of global addresses. And so we have a special form throughout the backend that guarantees the integrity of the intermediate pointers. But there's also another interesting problem, which is that when you get an OS exception, the kernel will have to save all of the registers to memory so that it's able to restore them later when it switches back to this process. And that's a problem because that exposes these intermediate values to an attacker if they actually have control over that kind of memory. So instead, what we did is we have a special convention with the kernel where we only use two registers, x16 and x17, for any of these sensitive values. That's something that we use in this sequence, but we also use it in all the other sequences that I talked about earlier. And so these are the four most important use cases that we have when you're trying to generate code for ARM64e. So there's a lot more, so you can talk to us later if you're interested. But to summarize, so ARM64e is an ABI for pointer authentication. So it's something that's based on the Darwin ARM64 ABI, and it extends it to provide control flow integrity. And so as John explained, the discriminator choice is really the key to hardening, but it's something that's really constrained by what the language provides. And at the compiler level, this has a bunch of interesting problems because now we have to preserve integrity of values. That's something that we don't often do in the backend. And so as John explained earlier, this is not ABI stable yet. We're still working on hardening it. And one step towards that is we sent out an RFC yesterday with all of our current patches, and we're hoping with your feedback we can make more progress. Thank you.
We have time for a couple questions, thanks. And please use the microphones that you find on the aisles.
Hi, so my question would be, you mentioned JIT at the beginning of the talk. So JIT, specifically JavaScript, does a lot of interesting things, like bailouts, where they actually forging the return address is the expected behavior. So what are your thoughts on this? Like, you planning to address it somehow, or like what in general are your thoughts on this?
What are you asking in particular? Like how do you provide additional protection against
Or do you think it's going to be a valid use case to use pointer authentication for something like a JavaScript engine?
I think you can use pointer authentication in a JavaScript. I mean, we do obviously. Like WebKit, Safari. These are things that we protect on iOS. You do have to, obviously, like anytime you have a JIT in the process, there's a lot of special hardening that you have to do again in the JIT, just because you are in fact have some ability to write executable instructions into memory, right? And so that's obviously, target number one for anybody who's looking to exploit your process, right? But yeah, pointer authentication does actually provide a lot of, it is at least a goal of pointer authentication to provide a lot of protection against the sorts of type confusion attacks that are very common against JavaScript engines, where like you have some sort of memory management bug with the JavaScript heap, and you like override an object, you manage to get a type confusion and right, you can basically synthesize the underlying memory representation for a JavaScript object and then convince the JavaScript engine to actually treat it as a JavaScript object. And that's just exactly the sorts of things that, this sort of basic memory corruption attack that partner authentication is designed to protect against. It's just that you also, of course, need to, think very carefully about how to protect the really core, code generation parts of the JIT. Those other things are things that are going to affect any sort of language implementation, any sort of interpreter, right? But it is still actually an incredibly important mitigation for them. And it's just, it's not, it doesn't solve all of their problems. None of this solves every problem, of course. But.
So I'm sorry we're out of time for further questions, but feel free to talk to the speakers afterwards. Thanks very much.